Hello everybody, and welcome to example 1 on page 151 of the workbook. We're going to work through our first example of finding a line of best fit using this method that we developed up in Theorem 6.12. Okay, so in this particular case, we are given some time and temperature data from Alma, Germany, the place where my wife grew up. Beautiful little town. You should visit it sometime. Okay, and looking at the table of data that we have here, we've got time in hours, okay, and then somebody's taking temperature readings for us, and the numbers are nice and round just to make this problem doable by hand here. And we'd like to find the line of best fit for the data. Okay, just to help us visualize it, we've got a graph of the data over here to the right. Okay, we're going to approach this the same way that we did in the derivation that we went through for Theorem 6.12. Okay, so if there were an exact solution to this problem, okay, if there were a line that went through all of those data points, then what it would mean, for example, is that the first data point, 1, 1, would have to lie on the line. Algebraically, that would be saying that 1 equals c times 1 plus d, and that would have to be true for all the rest of the data points. 2 equals c times 2 plus d, and so on until we get to the last one. 8 would have to be c times 5 plus d. Okay, we know that there's no exact solution to that equation, but it gets us started. Okay, if we rewrite that in matrix form, the same way that we did in our derivation, this would look like 1, 2, 3, 4, 5, a bunch of 1s times cd, okay, which is our candidate for the slope and the vertical intercept of our line, and over on the right-hand side would be our output values, 1, 2, 4, 5, and 8. Okay, so there's no exact solution to this system, but we're looking for the best approximation. Okay, and the theorem above tells us how to do that. Okay, we can turn this into a system of 2 by 2, or a 2 by 2 system by solving the system up here. And notice the things that we need to find in order to do that system are a star A and a star Y. We need to do those two calculations to get the ball rolling here. All right, so let's start with a star A. Okay, and a star is just the conjugate transpose of A. Okay, and A is the matrix that's sitting here. So we need to transpose that matrix and take complex conjugates, but in our case, all of the numbers are real. So taking complex conjugates doesn't change anything. All we need to do is transpose that matrix. Okay, so it's going to turn into this if we do that. Okay, and then we're going to multiply that by A. 1, 2, 3, 4, 5, 1, 1, 1, 1, 1. Okay, and if you do a dimension check here, see what we're going to end up with. We have a 2 by 5 matrix here and a 5 by 2, so sure enough, we're going to get a 2 by 2 matrix. Okay, and that confirms kind of what we said here, 2 equations and 2 unknowns in a minute. Okay, and I'll let you verify the calculations here. If you just use ordinary matrix multiplication, here's what you're going to end up with. Okay, just that 2 by 2 matrix. All right, and now we're ready to calculate the other piece, which is the a star Y. Let's do that below this. Okay, just in case we run out of space here, I want to conserve it a little bit. Okay, so a star Y, we just calculated a star above and got this matrix, 1, 2, 3, 4, 5, and then a bunch of 1s. And Y was our vector of right-hand sides, 1, 2, 4, 5, and 8. Okay, and I'll leave it to you to verify that if you do that calculation, you end up with a 2 by 1 vector that looks like 77 and 20. Okay, so again, the system that we're trying to solve looks like a star A times x naught equals a star Y. Okay, and if we write out that system using these two calculations that we did above, here's what it's going to look like. Our coefficient matrix over on the left is going to be 55, 15, 15, and 5. And then our right-hand side, let's write this as an augmented matrix. The right-hand side is going to be the 7720. That's the system that we're really talking about when we look at this equation over here. Okay, and that's an ordinary system, 2 equations and 2 unknowns. That's something that I trust that you could solve or have your calculator solve for you. And you're going to get x naught equals 17/10 and -11/10. Okay, and remember the significance of those two numbers that we found. They are just the C and the D, the slope and the vertical intercept of the best fit line. And so what we wind up with then is a best fit line that looks like this. 1.7, that's the 17/10 that's here, and then -11/10 is -1.1. Whoops, I forgot my variable. There's our line of best fit. Okay, and if I remember right, I think there was another part to this problem. Let's scroll up here for a minute. Okay, now that we have the line of best fit, they'd also like us to use it to estimate the temperature after 5.5 hours. Okay, so we're just going to take the value of time, substitute it in, and see what we get. So 1.7 times 5.5 minus 1.1. Do the arithmetic there, and we're going to get 8.25 degrees Celsius. Okay, and I think we've completed what they asked us to do in part A here. I'm going to just add one more calculation. This goes back to the derivation that we did. We're in a position where we could actually think about the error, okay, in this estimation that we did. Okay, I'm just going to write that out briefly, and you can maybe check my details and make sure that my algebra is right. If we wanted to get a feel for the error here, we could just write out its definition. Hang on a second here. Okay, and I'm really just copying down, okay, what all of these pieces are. Okay, if you do that matrix multiplication and then take the norm squared, what you will come up with is just 1.1. It just gives us an idea of how good this line of best fit is for our data. Okay, and in the next video, we will complete this problem, do part B of it.